Go over some resonance problems here that were assigned as homework. So you want to draw resonance structures for the following molecules. Step 1 is to add missing lone pairs onto heteroatoms. And so we'll do that here. Oxygen's divalent needs 2 lone pairs. And then what you'll need to do is use curved arrows to show the movement of electrons. You want to try to recognize a pattern. Here we have a pi bond, or a carbon-oxygen double bond, and we have lone pairs next to that. So we're going to move these over here to make a pi bond there instead, and move these electrons up here. Okay? And that will give us, after we draw the nice little resonance arrow, a molecule that looks like this. I'm going to draw this bond to an H here. I'm going to put the lone pairs that, I'll put all the lone pairs in there. And then now I'll do formal charges. There needs to be a plus at the foot of this arrow here. Not too familiar with this note-taking thing here. So plus here and minus here. Okay. Go to a smaller. All right, so draw resonance structures for the following molecules. So we've got lone pairs once again next to pi bonds. There's a pi bond here. And so we want to take these electrons here, swoop them down, and push them over to this third position. So there's always going to be 3 players involved. Electrons come from atom 1 and end at atom 3. So let's just draw that in. So the 2 electrons end up on that carbon atom, and it's going to have a formal charge of negative, and they came from this oxygen, so they're going to be positive. Okay, let's draw those pi bonds in. Now what you'll see is that there's also a 3-atom kind of pattern here. There's a lone pair at carbon 1 and a pi bond at carbons 2 and 3. So we want to move those curved arrows, or move those electrons in and push them over to carbon 3. And we will get a new resonance structure with a negative formal charge at that orange labeled carbon 3. Okay. And we want to repeat this process keep going around the ring. And the final movement would look like this. And we would get to this molecule here. Okay. Let's do some more curved arrows here. Ketones. So you always want to move the arrow to the oxygen because it's more electronegative. Carbon with only 3 bonds and no lone pairs of electrons is formal charge of +1, and oxygen with just 1 bond and 3 lone pairs is formal charge of negative. So we've got a nitrogen with a lone pair. Add those lone pairs in. You complete the octet for your heteroatoms, nitrogen and oxygen. And this guy here, we've got a lone pair. Right next to the carbocation, or positive charge carbon. Now here we can do 2 different things. We have a pi bond next to a positive, and we have a lone pair next to a positive. So it might be difficult to draw both of these at the same, on the same structure. So I'm going to draw out the molecule, copying it below. And in the top case, I'm going to move the pi bond. Pi bonds next to positive charge is a pattern that's very commonly occurring in the organic chemistry class. And you can put the plus here. or you could move the electrons from the nitrogen atom over to make this structure here. Okay. Now, just thinking ahead, this is going to be the major contributor to the overall resonance hybrid because every atom has an octet. These other resonance structures are valid, but not major. Okay. All right, let's go to page 2 here, if I can find it. Okay, I didn't put it in, so let's go ahead and grab that. Oops. All right, so let's work on these now. We again have that same situation where we have a pi bond and we have lone pairs next to the positive charge here. So we could do 2 possible moves. All right, one move is to take these lone pairs and bring them in to make a pi bond, and that would be the major contributor, all octet on every atom, and it's no charge separation, more pi bonding. The other move we could do is take those pi electrons and move them in to form a pi bond towards the top of this molecule, and there would be a positive charge here on this carbon here. It's really hard to draw these things with this drawing program. Now here we have a positive charge next to a pi, and there's also a pi bond over here. So you can do several different curved arrows to show how the pi bonding electrons can move around. So we could move to the right, we could move to the left a couple times. Okay. And we could move this pi bond. So these guys are called conjugated alkenes, and they have a ton of resonance structures available to them. It's one of the reasons that tomatoes are red and carrots are orange, but you'll learn about that later. Here, we want to think about a lone pair next to a pi bond. So take these electrons, swoop them in, and now that looks like a carboxylic acid, so that's the major contributor. This guy here, we have 2 possibilities because we have lone pairs next to a pi bond on the left and a lone pair next to a pi bond on the right. So we can just show the curved arrows going like that. Adding lone pairs, it's optional for those of you who might not be too familiar with the valency of different atoms. Okay, so that would be one movement, right? A lone pair next to a pi bond. The other movement would be moving these lone pairs next to this pi bond on the right up to the nitrogen, and that will make yeah, I always put in those resonance arrows. We will make this structure here. Yeah, so which of these is the major resonance contributor? So we have the starting structure, we have this structure that I generated, and this structure that I generated. Now all of these have 2 pi bonds, right? 2, 2, 2. and they have a negative charge, negative, negative, negative. And so what's different about them? Well, the one right here, mark it red, I guess, has a negative on oxygen, and oxygen is more electronegative, so that's going to be the major contributor to the overall resonance hybrid. Things to think about, okay? Now this guy here is just like the phenol molecule that I messed around with previously. You have lone pairs next to pi bonds, and you start off by moving them around, okay? So look at that problem to see how to do this one. Let's go to the next page here. All right, so let's do some more resonance structures for these. So for this one, there's no lone pairs. There is a lone pair on the pi bond, but that's not going to help us. What we want to do is simply just break the pi bond, okay? That makes a carbon with a positive charge, an angry guy without an octet, and up here we have just 2 bonds to nitrogen, so it has a negative charge. Over here we have a lone pair next to a pi bond, so we want to utilize that pattern to generate another contributor to the resonance hybrid. I'll add the lone pairs in there. Okay. This guy here, we've got a pi bond next to a empty p orbital, and so that would be the simple move there. Same thing here. This guy here, you have 2 possibilities, right? You got lone pairs here, and here you have a pi bond, okay? So, sorry, I drew all over that. We'll erase that so I don't confuse my arrows and notation with what I'm going to do. So let's first move the pi bond in to show one possible resonance structure. Okay, and I've messed that up. Okay, so there we go. Now another possibility is to move, and again we're moving lone pairs, so you might have to draw those in. These lone pairs on oxygen swoop in, and what you'll get is a carbon-oxygen pi bond. And this is great. This is going to be the major resonance structure because there's no charge separation, there's more pi bonding. Every atom has an octet. Let's do the next one. Alright, so in this one we've got a positive charge, so that means a p orbital that's available to it for pi bonding, and we've got the oxygen here. So remember, whenever a carbon has 3 bonds, you move the arrow towards that direction if possible. Okay, this carbon has 3 bonds. I'm not drawing the H's, I'm not even drawing the C. But anyways, we draw that arrow. Here again, same situation. We've got opposites attract, right? So here's lone pair on oxygen. It comes in and makes a pi bond to this carbon, satisfying the octet. Okay, same thing here. So this definitely would be the major resonance structure. I'm not going to mess around with the pi bonds, but you could also move the pi bonds. I'm not going to show that here. Here's a nitrogen with a lone pair. Draw in the lone pair so you can see that. Nitrogen normally has 3 bonds and a lone pair on it, and a carbon normally has 4 bonds. So this is a match made in heaven. It's an octet, more pi bonding. It's the major contributor to the overall resonance hybrid. This too, recognize those carbons with only 3 bonds and swoop in those electrons to satisfy its octet. Yes, the positive charge as a result, I'm sorry I forgot it up here, does move around, okay? Now this one you're thinking, well, there's no charges, what do I do? Well, the pi bond, right? Always utilize the pi bonds or lone pairs in resonance. There's only one real move that you can do with a ketone, or this is an aldehyde, right? And that's to move the electrons up to the more electronegative oxygen. And so this is bad, you know, this would be the major resonance structure, and this would be the minor, but that's the only thing we can draw here.